Imagine standing somewhere near the center of modern North America, perhaps on the open plains of Kansas, Nebraska, or the Dakotas. Today, the horizon seems almost endless. Fields and grasslands stretch beneath a broad sky, crossed by roads, rivers, farms, and quiet towns. There is no coastline for hundreds of miles. The nearest ocean feels impossibly distant. Yet beneath this familiar landscape lie the remains of another world. The rocks under these plains contain the shells of ammonites, the teeth of sharks, the bones of enormous marine reptiles, and the microscopic remains of organisms that once drifted through warm seawater. They reveal that the heart of North America was not always dry land. During the Cretaceous period, an immense inland sea spread across the continent, eventually connecting waters near the Gulf of Mexico with those of the far north. At its greatest extent, this seaway stretched for thousands of miles and divided North America into two separate landmasses. But this transformation did not begin with a sudden flood. There was no single day when the ocean broke through and covered the continent. No enormous wave crossed the plains. No creature could have watched the entire change take place. The birth of the Western Interior Seaway was a process measured not in hours or years, but in millions of years. It emerged from the combined movement of continents, the changing shape of Earth's crust, and a global ocean standing far higher than it does today. To understand how an ocean could appear in the middle of a continent, we must return to a time nearly 100 million years ago. The world of the Cretaceous was already ancient beyond ordinary human imagination. Dinosaurs had existed for well over 100 million years. Birds had begun evolving from feathered dinosaur ancestors. Flowering plants were spreading into landscapes that had long been dominated by conifers, cycads, ferns, and other older plant groups. Mammals existed too, although most were still small and lived quietly among much larger animals. The continents were recognizable in outline, but none occupied exactly the positions they hold today. The Atlantic Ocean was much narrower. North America was continuing to separate from Europe and Africa as new oceanic crust formed along the growing Atlantic basin. South America was also moving away from Africa, gradually opening the South Atlantic. India remained far from Asia, moving northward across a vanished ocean, while Australia was still connected to Antarctica. Earth's surface was changing continually, although almost all of that movement was far too slow to be noticed by anything alive. North America itself was being shaped by powerful forces along its western edge. An oceanic plate was moving beneath the continent in a process called subduction. As the dense oceanic crust descended into Earth's interior, it compressed and deformed the edge of North America. Mountains rose in the west, although they were not yet the modern Rocky Mountains familiar today. These older mountain-building events created elevated landscapes, volcanic regions, and belts of folded rock extending through parts of what would eventually become the western United States and Canada. Yet the effects of this collision were not limited to the coast. The immense weight and pressure associated with mountain building caused a broad region farther inland to bend downward. The continental crust is solid rock, but across enormous distances and geological timescales, it can flex. Imagine placing a heavy weight near the edge of a long wooden board. The area beneath the weight sinks, but part of the board farther away may bend as well. Something similar happened across western and central North America. A long, shallow depression developed east of the rising mountains. Geologists describe such a feature as a foreland basin. It did not resemble a narrow valley or a sudden trench. Instead, it was an enormous region of gradually lowered land stretching across much of the interior of the continent. In many places, the difference between dry ground and the future seafloor may have been only a relatively small change in elevation. This broad depression alone was not enough to create the inland sea. The oceans also had to rise. During much of the Cretaceous, Earth was far warmer than it is today. The planet had no large permanent polar ice sheets comparable to those now covering Antarctica and Greenland. Water that would otherwise have been stored on land, as ice remained within the oceans. But the absence of ice was only part of the explanation for the unusually high seas. The ocean basins themselves were different. Underwater volcanic ridges were forming new seafloor at unusually high rates. These young ridges were warm and elevated, occupying more space within the ocean basins and leaving less room for seawater. When the capacity of the ocean basins decreased, water spread outward over the low edges of the continents. Across the Cretaceous world, shallow seas covered immense areas that are now dry land. Europe was partly transformed into an archipelago of islands. Shallow seas extended across portions of Africa, Asia, and South America. North America, with its low interior basin, was especially vulnerable to the advancing water. At first, the change would have appeared along the margins of the continent. From the south, marine waters connected to the ancient Gulf of Mexico began moving northward across low coastal plains. From the far north, water from the Arctic region advanced southward. These were not yet the two ends of one continuous sea. They were separate marine incursions entering the continent from opposite directions. The coastline shifted repeatedly. During periods when relative sea level rose, water moved farther inland. Geologists call this a marine transgression. When the water retreated and land reappeared, it was a regression. These advances and retreats occurred many times throughout the history of the seaway. The Western Interior Sea was never a perfectly fixed body of water with an unchanging shoreline. It expanded, narrowed, withdrew, and returned as sea level, sediment supply, and the elevation of the land changed. A place might remain beneath shallow water for thousands of years, slowly collecting mud and the remains of marine organisms. Later, the sea could withdraw, exposing broad tidal flats and coastal plains. Rivers would cross the newly emerged ground, carrying sand and silt from the western mountains. Then the water might return again, covering those river deposits with another layer of marine sediment. These repeated movements were written into the rocks. Layers of sandstone often preserve ancient beaches, river channels, and shallow coastal environments. Shale commonly formed from mud settling in quieter, deeper water. Chalk and limestone developed where enormous quantities of microscopic marine remains accumulated on the seafloor. By reading the order and composition of these layers, geologists can reconstruct shorelines that disappeared tens of millions of years ago. Before the sea reached its greatest size, the interior of North America was a vast and varied landscape. Rivers flowed eastward from the rising mountains. They crossed floodplains, divided into branching channels, and deposited sand and mud across low ground. Forests grew along the rivers and on better drained land. Conifers remained important, but flowering plants were becoming increasingly common and diverse. Ferns and other vegetation covered moist areas. Insects moved among the leaves, while dinosaurs traveled through environments that would eventually vanish beneath the sea. The climate was generally warm, but the continent was not uniform. Seasonal rainfall, river flooding, coastal storms, and periods of drought shaped different regions. Near the advancing ocean, freshwater marshes gave way to brackish lagoons where river water mixed with seawater. Tidal channels wound through low vegetation. Mudflats appeared and disappeared with changing water levels. Beyond them lay sandy barriers and shallow bays. This boundary between land and ocean was never still. As the sea advanced, trees growing near the coast died when salt water reached their roots. Storms eroded exposed shorelines. Waves rearranged sand into bars and beaches. Rivers deposited sediment into the water, sometimes building deltas outward and briefly reclaiming land from the sea. Elsewhere, rising water overwhelmed the river mouths and converted their valleys into long estuaries. The transformation would have been almost invisible from one generation to the next. An animal born near a coastal forest might live its entire life without noticing any permanent change. Its descendants, thousands of generations later, might inhabit a marsh where that forest once stood. Far more generations later, the same location could lie beneath open water, with fish swimming above sediments that still contained buried roots and leaves. The sea moved at the pace of geology. It advanced across landscapes that had existed for millions of years. Hills became islands. River valleys became bays. Floodplains disappeared beneath shallow water. The coastline migrated so far inland that places now near the geographical center of the continent eventually stood beside a marine horizon. As northern and southern waters moved toward one another, the remaining stretch of land between them narrowed. The exact shape of the sea changed repeatedly, and connections may have formed, weakened, or temporarily disappeared as shorelines shifted. Eventually, however, the marine waters of the North and South became linked across the interior of North America. A continuous seaway had formed. At its maximum extent, it ran for roughly 3,000 miles from the region of the Gulf of Mexico toward the Arctic Ocean. In some intervals, it spread at least 1,000 miles across. Its western shoreline lay near the rising highlands, while its eastern waters extended across parts of the Central Plains. Much of what is now Texas, Colorado, Wyoming, Montana, Kansas, Nebraska, the Dakotas, and the Canadian interior was influenced or covered by its waters at different times. The continent had been divided. To the west lay a long, relatively narrow landmass now called Laramidia. It included portions of what would become Western Canada, the United States, and northern Mexico. To the east lay Appalachia, a larger landmass that included much of eastern North America. The names are modern scientific terms. No permanent lines separated these lands throughout the entire Cretaceous because the sea repeatedly changed in width and extent. But for long intervals, animals and plants living on opposite sides were divided by an enormous marine barrier. The sea between them was shallow when compared with the great ocean basins, but it was far from being a simple flooded plain. Some regions held only relatively shallow coastal water. Others descended hundreds of feet or more. Currents moved through the long marine corridor. Rivers entered from both sides, carrying fresh water, sediment, and nutrients. Water from southern and northern sources met within the basin, creating changing temperatures, salinity, and circulation patterns. At first, this newly connected sea may have seemed almost empty when viewed from high above, a broad surface of water extending beyond the horizon, broken by distant coastlines, islands, river mouths, and passing storms. But beneath the surface, life was already gathering. Microscopic plankton drifted through the sunlit upper waters. Shellfish lived on and within the seafloor. Fish entered the expanding habitats. Ammonites, sharks, turtles, diving birds, and marine reptiles would eventually occupy this immense environment. Food chains grew more complex as the seaway expanded and changed. For millions of years, the interior of North America would belong not to herds crossing open plains, but to creatures swimming through warm water. The quiet sediment settling onto the bottom would preserve their remains. Shells would be buried in mud. Teeth would fall into darkness. Skeletons would sink, break apart, and sometimes survive long enough to become fossils. Layer after layer would accumulate, creating the rocks that now rise from modern fields, badlands, cliffs, and dry river valleys. The plains of the future were becoming a seafloor, and across the center of the continent, where highways and farms would one day stretch beneath an open sky, the first broad waves of the Western Interior Seaway rolled over drowned land. The new sea did not resemble a narrow river cutting through the continent. It was an immense marine corridor, wide enough in many places for neither shore to be visible from its center. Its waters stretched across regions that would one day become plains, farms, towns, and cities. Where dry land had once connected eastern and western North America, a moving expanse of waves now opened beneath the Cretaceous sky. Yet the Western Interior Seaway was never one simple, unchanging body of water. Over its long existence, its boundaries shifted again and again. At times, the sea expanded so widely that it covered much of the continent's low interior. During other intervals, it narrowed into separate basins or withdrew hundreds of miles from former coastlines. Some areas were repeatedly submerged and exposed, leaving behind a layered record of deep water, shallow bays, beaches, river deltas, swamps, and dry coastal plains. The sea seemed permanent to every creature living beside it, but across geological time, it was always in motion. Along its western margin, the coastline lay near a vast belt of rising mountains and highlands. Rivers descended from these elevated regions, carrying enormous quantities of eroded rock toward the sea. Gravel remained in faster channels closer to the mountains. Sand spread across riverbeds, deltas, beaches, and nearshore shallows. Finer mud traveled farther from land before settling through the water. The western shoreline was therefore continually being rebuilt. A river could push a delta outward into the sea, creating new wetlands and low islands. Waves and currents could then erode the fresh sediment, carrying it along the coast or dispersing it into deeper water. When sea level rose, the coastline moved back across the delta. When the sea withdrew, rivers advanced again across the newly exposed seafloor. The result was not a clean border between land and ocean, but a broad and complicated coastal world. There were tidal flats crossed by shallow channels, sheltered lagoons lying behind sandy barriers, brackish marshes near river mouths, and open beaches facing the interior sea. Some shorelines were muddy and low, others were lined with sand. Forests grew within sight of marine water, and dinosaur tracks were sometimes impressed into damp coastal sediment that later hardened into stone. Farther east, the landscape was generally lower and contributed less sediment than the mountainous west. The eastern shoreline could be broad and gently sloping, allowing relatively small changes in water level to move the coast great distances. A rise of only a limited amount could flood an enormous area when the ground was almost flat. This helped give the seaway its remarkable size. Although it connected northern and southern marine waters, it was not a deep ocean basin like the modern Atlantic. Much of it covered continental crust and was comparatively shallow. Depth varied from place to place and changed over time. Coastal areas might have been only a few feet deep, while central portions descended hundreds of feet beneath the surface. Even in its deeper regions, sunlight illuminated the upper waters. Below that bright layer, the sea became dimmer and cooler. Fine particles descended slowly toward the bottom, where they accumulated in quiet layers. In some places, the seafloor was disturbed by burrowing animals and bottom-feeding creatures. Elsewhere, poor circulation and low oxygen made the bottom difficult or impossible for many organisms to inhabit. The sea's enormous length created unusual conditions. Its southern entrance opened toward warm subtropical waters connected with the Gulf of Mexico and the wider Atlantic realm. Its northern end reached toward the cooler Arctic region. Water entering from opposite directions could differ in temperature and salinity. Winds, tides, river discharge, and changes in sea level all influenced how these waters moved and mixed. The precise circulation of the seaway changed during its history and remains a subject scientists reconstruct from rocks, fossils, and chemical evidence. It was not governed by one permanent current, flowing steadily from north to south or south to north. Instead, circulation likely varied with the width and depth of the marine connections, the position of shorelines, seasonal winds, and the amount of fresh water entering from the continent. At times, the connection between the northern and southern oceans may have allowed stronger exchange. During narrower phases, circulation could become more restricted. Water in some deeper regions may have remained isolated long enough to lose much of its oxygen. Rivers constantly carried fresh water into the sea. They also brought clay, sand, dissolved minerals, plant remains, and nutrients washed from the surrounding land. Near major river mouths, the surface water may sometimes have been less salty than the water below. Muddy plumes extended outward after floods, coloring the sea and delivering sediment far from shore. The western rivers were particularly important because they drained actively rising and eroding terrain. Their sediment formed a thick wedge along the western side of the marine basin. Over millions of years, these deposits accumulated into layers thousands of feet thick in some regions. Each layer preserved a different part of the changing coast. Coarse sandstone could mark an ancient beach or river channel. Thinly layered mudstone and shale formed where fine sediment settled in quieter water. Coal developed from vegetation accumulating in coastal swamps during times when the sea had temporarily retreated. Marine shells found above such coal might reveal that the water later returned and drowned the swamp. In this way, a cliff exposed in the modern West can contain an entire sequence of vanished environments. At its bottom may lie rock formed beneath offshore water. Above it may be sandstone from a shoreline that advanced over the old seafloor. Higher still may appear mud from a lagoon, coal from a coastal swamp, and river sediment from a period when the land extended farther east. Another marine layer above them can show that the sea returned once again. The rock does not preserve a frozen landscape. It preserves movement away from the sediment-rich western coast. Different materials settled onto the seafloor. In parts of the open seaway, the water contained countless microscopic organisms. Some produced tiny plates or shells made from calcium carbonate. After death, their remains sank and accumulated in enormous quantities. Over time, this pale biological sediment became chalk. The white and cream-colored chalk deposits now exposed in parts of Kansas and elsewhere are among the clearest reminders of the ancient sea. They formed not from ordinary sand washed from land, but largely from the microscopic remains of marine plankton falling through the water over immense periods. A handful of chalk may contain the compressed remains of countless organisms too small to have been seen without magnification. The accumulation was extremely slow when measured against a human lifetime, yet the process continued for hundreds of thousands and millions of years. Tiny particles settled day after day, gradually burying shells, teeth, bones, and other remains resting on the bottom. The color and composition of the seafloor varied according to local conditions. Near shore, sediment was often darker and richer in land-derived mud. Farther from rivers, pale carbonate material could dominate. In poorly oxygenated water, organic matter sometimes survived instead of being completely consumed by decay. These dark, organic-rich deposits later became important source rocks associated with petroleum. But the sea was not merely a quiet basin collecting sediment. Storms moved across its surface. The Cretaceous climate was warm, and the long north-south seaway offered a broad path for weather systems. Powerful winds could build waves over great distances. Near the coast, storms rearranged beaches, flooded low ground, breached sandy barriers, and carried marine sediment into lagoons and marshes. The shallow nature of much of the seaway could make storm waves especially destructive along exposed coasts. A calm shoreline might change within hours. Waves could tear into a beach, uproot vegetation, and scatter shells across the seafloor. Storm surges push saltwater into river mouths and low coastal plains. Afterward, the sea would settle again, leaving behind new sand layers and debris. Far offshore, storms still affected the upper water. Wind mixed the surface and changed local currents. Dead organisms and floating material were carried in new directions. Fine sediment stirred from shallower bottoms could remain suspended before settling somewhere else. Seasonal weather also shaped the sea. Sunlight warmed the surface during long Cretaceous days. Evaporation increased salinity in some areas, while rainfall and river discharge reduced it near the coast. Differences in temperature and density could produce layers within the water. When those layers mixed, oxygen and nutrients moved through the sea. When they remained separated, deeper water could become stagnant. The seaway therefore contained many environments rather than one uniform habitat. Its shallow edges were bright and energetic, influenced by waves, tides, rivers, and storms. Sheltered bays offered quieter water and muddy bottoms. Offshore regions were more stable, although currents and seasonal changes still reached them. Deeper basins could become dark and oxygen poor. Sandy seafloors existed in some places, soft mud in others, and pale carbonate sediment elsewhere. Even the temperature was not identical throughout its length. Southern waters were generally warmer, influenced by low-latitude seas. Northern regions experienced cooler conditions and stronger seasonal differences. As the coastline shifted, a location might pass through several climatic and marine settings without moving at all. A region first lying near a northern bay could later become part of a broad central sea. Millions of years afterward, it might lie close to a retreating southern shoreline. The fossils and minerals preserved there would record these changes. Islands and areas of higher ground remained above water, within or near the seaway at different times. Some were extensions of older geological structures that the sea did not completely cover. Others may have appeared temporarily as water levels fell. These patches of land created local coastlines and influenced currents, sediment, and animal movement. From such islands, the sea would have filled nearly the entire horizon. The nearest mainland might have been invisible beyond the curve of the water. Flying reptiles and early birds crossed above the waves. Driftwood traveled far from the coast. The carcasses of land animals could occasionally be carried outward by rivers or storms, eventually sinking into marine sediment. The presence of dinosaur remains within marine rocks does not mean that dinosaurs lived in the open sea. Some died near rivers or coastlines and were washed into the water. Their bodies drifted or sank, becoming rare visitors to an ecosystem dominated by marine life. Along the coast, however, the boundary between the two worlds was close. Dinosaurs moved across beaches and floodplains, while sharks and large fish swam in nearby water. Turtles rested near shore. Crocodile-like reptiles occupied rivers, estuaries, and coastal environments. Insects flew above marshes, and flowering plants grew beside channels influenced by the tide. The inland sea did not isolate land from water completely. It created thousands of miles of new coastline where the two environments met. These coastal habitats were among the most productive parts of the Cretaceous continent. Rivers delivered nutrients from the land. Shallow sunlight supported microscopic life. Small fish gathered in protected water, and larger animals followed them. Mudflats and lagoons offered food and shelter to creatures adapted to changing salinity and water levels. Farther offshore, a different food system was developing. Microscopic algae and other plankton captured energy from sunlight. Tiny drifting animals fed upon them. Fish consumed the smaller organisms, while larger predators hunted the fish. Shell-bearing cephalopods moved through the water, and animals living on the bottom filtered food or searched through soft sediment. The entire sea was supported by processes that were almost invisible from its surface. Sunlight entered the upper water. Nutrients rose from depth or arrived through rivers. Plankton multiplied. Bodies sank. Sediment accumulated. Currents carried life and minerals from one region to another. Through these slow exchanges, The new sea became capable of supporting one of the most extraordinary marine communities in North American history. But the Western Interior Seaway was still changing. As the water deepened and widened, open marine conditions spread across areas that had once been coastal. New species entered from the south and north. Some found favorable environments and multiplied. Others remained limited to particular temperatures, depths, or regions. The sea became both a passage and a barrier. Marine creatures could travel through the center of the continent between distant oceanic regions. Land animals, however, faced an expanse of salt water separating the eastern and western shores. Populations that had once been connected were divided. Over millions of years, this separation would influence the evolution of life on both sides. From the coast, none of this larger pattern could be seen. There was only the sound of waves, the movement of tides, and a horizon of water where forests and rivers had once continued uninterrupted. Storm clouds crossed the distance. Sediment darkened the water near river mouths. Far offshore, the sea changed from brown to green, and then to a deeper blue. Beneath that surface, the basin was filling with life. The first great communities of fish, sharks, ammonites, turtles, and marine reptiles were taking shape. Soon the inland sea would become a world of vast migrations, deep water hunters, armored shells, and predators capable of dominating nearly every part of its waters. For now, however, the sea itself remained the greatest presence of all, a long, restless corridor dividing a continent, reshaping its shores, and slowly building the stone record of a world that would remain hidden beneath the plains for tens of millions of years. From the surface, the Western Interior Seaway might often have appeared almost empty. On calm days, its water stretched toward a distant horizon beneath a warm Cretaceous sky. Wind moved across the surface in long, dark bands. Small waves rose and faded. Far from shore, there were no trees, islands, or mountains to provide a sense of distance. There was only open water, sunlight, and the slow movement of clouds. But beneath the surface, the sea was crowded with life. Nearly every large creature that swam through these waters depended upon organisms too small to be seen clearly. In the bright upper layers, microscopic algae and other photosynthetic plankton absorbed energy from the sun. They formed the foundation of a vast food network extending from tiny drifting animals to some of the most powerful predators of the Cretaceous. These plankton did not live evenly throughout the sea. Their abundance changed with sunlight, temperature, currents, and the availability of nutrients. Near river mouths, water arriving from the continent carried dissolved minerals and organic material. In other regions, currents brought nutrients upward from deeper water. Where conditions were favorable, microscopic life multiplied in enormous numbers. The surface could become a living layer. Tiny organisms drifted with the currents, unable to resist the movement of the sea. Some lived only briefly. Others produced protective shells or plates of calcium carbonate. When they died, their remains began a slow descent toward the bottom. Most disappeared during that journey. They were eaten, dissolved, or broken apart before reaching the seafloor, but countless others survived long enough to settle in the mud. Over immense periods, their pale remains accumulated into deposits that would eventually harden into chalk. The chalk cliffs and formations now found across parts of the Great Plains began as a continuous rain of microscopic bodies falling through ancient seawater. Above the bottom, clouds of tiny animals fed on the plant-like plankton. Small crustaceans and other drifting creatures moved through the water in numbers impossible to count. They were eaten by small fish, young cephalopods, and filter-feeding animals. Those creatures, in turn, became prey for larger hunters. Energy passed upward through the sea, one body at a time. In the shallow coastal waters, sunlight reached the sea floor. Oysters and other shellfish attached themselves to firm surfaces or gathered in dense communities. Clams lived within soft sediment. Snails moved slowly across the bottom. Sea urchins fed among the mud and sand, while worms and small crustaceans burrowed beneath them. The seafloor was marked by constant, quiet activity. Animals created tunnels, resting traces, feeding marks, and narrow paths through the sediment. Some waited beneath the surface for food to pass overhead. Others filtered particles directly from the water. Shells accumulated where currents carried them, sometimes forming thick beds that later became part of the fossil record. Not every part of the seafloor was equally hospitable. Where oxygen circulated freely, bottom-dwelling communities could become diverse and abundant. In deeper or poorly mixed areas, oxygen levels sometimes fell. Few animals could survive for long under such conditions. The bottom became quieter, darker, and less disturbed. This difference affected what would later be preserved. In well-oxygenated areas, scavengers consumed dead bodies and burrowing animals disrupted the sediment. Skeletons were often scattered before burial. In low-oxygen environments, fewer creatures reached a carcass, and the mud remained relatively undisturbed. Under rare circumstances, more complete remains could survive long enough to enter the geological record. Most living things, however, left no recognizable fossil. Soft tissue decayed, small bones were broken apart, shells dissolved, teeth were lost and scattered. The fossils discovered today represent only a tiny and incomplete sample of the creatures that once lived in the sea. Among the most common and recognizable inhabitants were ammonites. Ammonites were cephalopods, distant relatives of modern squids, octopuses, cuttlefish, and nautiluses. Their bodies occupied the outer chamber of a coiled shell, divided internally into smaller compartments. By regulating gas and liquid within those chambers, they could control their buoyancy and move through the water without sinking to the bottom. Their shells appeared in an extraordinary range of forms. Many were tightly coiled into flat spirals. Some were broad and rounded, while others were narrow and compressed. Their surfaces could be smooth or decorated with ribs, ridges, and rows of small projections. Certain Cretaceous ammonites abandoned the familiar spiral almost entirely, producing shells that curved loosely, bent into hooks, or formed unusual open shapes. These strange forms were not errors or deformities. They belonged to successful groups that survived for millions of years. Some ammonites remained relatively small. Others grew shells several feet across. Their exact behavior cannot be watched directly, and scientists must reconstruct it from shell structure, muscle attachments, living relatives, and the environments in which their fossils occur. Many probably moved by drawing water into the body and forcing it outward through a muscular tube. This jet propulsion allowed them to change position, escape danger, and search for food. Their movements were likely more controlled than fast. The large shell provided protection and buoyancy, but it also created resistance in the water. Ammonites occupied many levels of the marine food web. Smaller forms may have fed on plankton and tiny animals. Larger species could have captured crustaceans, juvenile fish, and other prey with their tentacles. At the same time, ammonites themselves were eaten by fish, sharks, marine reptiles, and other cephalopods. Their shells offered protection, but not complete safety. Fossil ammonites sometimes preserved damaged areas that healed while the animal was still alive. These scars show that some individuals survived attacks. Other shells bear holes or broken edges that may record the final moments of an unsuccessful escape. The sea also contained more familiar-looking cephalopods. Squid-like animals moved through open water without large external shells. Some possessed internal supports that occasionally fossilized. Their soft bodies rarely survived, leaving a much poorer record than the hard shells of ammonites. Yet they may have been abundant and ecologically important. They were swift, flexible hunters with well-developed eyes and arms surrounding the mouth. They could seize small fish and crustaceans. They could also become prey almost instantly. In a sea filled with larger hunters, speed and awareness were essential. Fish occupied nearly every accessible habitat. Small schooling fish moved through the sunlit water, feeding on plankton and smaller animals. Their numbers made them one of the most important connections between microscopic life and large predators. A single fish was a small meal, but a dense school represented an enormous concentration of energy. The schools changed shape as they moved. Thousands of bodies turned almost together, reflecting light from their scales. When threatened, the group tightened, divided, or rushed toward deeper water. This behavior reduced the chance that any one fish would be taken, but it also attracted attention from hunters capable of driving directly into the mass. Other fish remained near the bottom. Some searched the sediment for shellfish and crustaceans. Others waited in stillness before striking. Coastal species entered lagoons and estuaries, tolerating water that became less salty near rivers. Open water species traveled across broad regions of the seaway. The fish communities changed throughout the Cretaceous. Species appeared, spread, and vanished as the sea expanded and retreated. Animals from southern waters entered during periods of strong connection with the Gulf region. Other forms arrived from the north. Some may have adapted to conditions found only within the interior sea. Among the most distinctive fish were the large predatory forms that lived far above the seafloor. Pachyrhizidus was a powerful fish with a streamlined body and strong jaws. Different species varied in size, but some grew large enough to hunt other substantial fish. Its shape suggests an active swimmer capable of moving through open water rather than remaining close to the bottom. Enchotus was usually smaller, but its appearance was formidable. It possessed long, sharp teeth, including enlarged fangs near the front of the mouth. Despite its frightening anatomy, many species were not enormous. Enchotus filled a middle position in the food web, a hunter of smaller animals that could itself be swallowed by much larger predators. Its fossils have been found not only as isolated remains, but sometimes within the stomach regions of larger fish and marine reptiles. This reveals one of the most important truths about the seaway. Almost every hunter was also potential prey. A fish might spend its life pursuing smaller animals while avoiding attacks from above, below, and behind. Size provided protection only until something larger arrived. Few fish represented this principle more dramatically than Xiphactinus. Xiphactinus was one of the most famous inhabitants of the Western Interior Seaway. It had a long, powerful body, a large head, and jaws lined with prominent teeth. Large individuals reached lengths of more than 15 feet, making them comparable in size to some modern predatory sharks. It was not a shark, but a giant bony fish. Its body was built for movement through open water. The deeply forked tail provided propulsion, while the relatively narrow body reduced drag. Its jaws opened widely, allowing it to seize prey of remarkable size. Xiphactinus may have attacked by accelerating toward a target and closing its jaws around it. Smaller fish could be swallowed whole. Larger prey might be injured, repositioned, and consumed in sections. Although the precise feeding behavior remains uncertain, one extraordinary fossil preserves a large Xiphactinus with another fish inside its body. The swallowed animal was several feet long and remained nearly complete. The predator apparently consumed it whole. It then died before digestion had progressed far enough to destroy the meal. The cause of death cannot be established with certainty. The prey may have damaged internal organs. It may simply have been too large to process safely. Another event may have killed the predator soon after feeding. Whatever happened, the fossil captured a rare moment in the life of the ancient sea. It shows both the ambition and danger of predation. Even a powerful hunter could make a fatal mistake. Xiphactinus was not the only large fish in these waters. Other predatory species competed for prey, occupied different depths, and followed schools across the sea. Juveniles of large species would have faced very different dangers from adults. Before reaching their full size, they could be hunted by sharks, larger fish, and marine reptiles. Growth itself was a long period of vulnerability. Sharks were already ancient by the time the Western Interior Seaway formed. Their evolutionary history extended hundreds of millions of years into the past. They entered the new inland waters as members of many different lineages, not as a single uniform type of predator. Some were relatively small and fed on fish, crustaceans, or bottom-dwelling animals. Others grew large enough to hunt substantial prey because shark skeletons consist mainly of cartilage. Complete bodies rarely fossilized. Teeth were different. Sharks continually lost and replaced them throughout life, leaving enormous numbers behind. A single animal could shed thousands of teeth over the years. These teeth now provide much of the evidence for the sharks that lived in the seaway. Their shapes reveal different feeding strategies. Thin, pointed teeth were effective for gripping slippery fish. Broader, cutting teeth could slice through flesh. Flattened teeth were suited for crushing shells. By comparing teeth with those of living sharks and examining wear patterns, paleontologists can estimate how different species fed. One of the best-known large sharks of the Cretaceous Seaway was Cretaceous. It had a streamlined body and a set of broad, sharp teeth capable of cutting into large animals. Large individuals may have reached lengths approaching 20 feet. Cretaceous hunted fish and marine reptiles. and fossil evidence shows that its bites could leave deep marks in bone. It occupied one of the highest positions in the food web before the largest mosasaurs became dominant. But even Cretaceous lived in a world of competition. Large predatory fish pursued some of the same prey. Marine reptiles entered the same hunting grounds. Scavengers gathered around carcasses. An injured animal could quickly become food for creatures it had once hunted. Death rarely remained private in the seaway. When a large fish or reptile died near the surface, the body might float for a time as gases formed within it. Sharks and smaller scavengers could remove flesh. Eventually, the remains sank. More animals fed upon them on the way down, and after they reached the bottom, bones separated as connective tissue decayed. Currents moved lighter elements. Teeth scattered into the sediment. Only rapid burial or unusually favorable conditions allowed a skeleton to remain largely intact. The majority disappeared into the ecosystem. Their bodies became food. Their nutrients returned to the water. Their remains were broken down and absorbed into new life. This continuous exchange connected every depth of the sea. The plankton at the surface supported small animals. Small animals fed fish. Fish fed larger fish, sharks, seabirds, turtles, and marine reptiles. Dead bodies nourished scavengers and bottom communities. Nutrients released from decay eventually returned to the sunlit water, where the cycle began again. Nothing in the sea existed alone. Even its greatest predators depended on organisms they never encountered directly. A giant hunter survived because sunlight had fed microscopic cells, because those cells had nourished drifting animals, and because generations of fish had transferred that energy through the food web. The immense scale of the Western Interior Seaway allowed these relationships to develop across millions of square miles. There were crowded coastal nurseries, open water feeding grounds, quiet muddy bottoms, oxygen-poor depths, and migration routes extending from warm southern waters toward the north. Every environment supported a different community, and every community changed as the sea itself changed. Above them all, the coastline continued its slow movement. Rivers delivered new sediment. Storms disturbed the shallows. Sea level rose and fell. Habitats shifted across the continent, and the animals followed where they could. By now, the Western Interior Seaway had become far more than water dividing two lands. It was a complete living world. Its smallest inhabitants were building chalk from their remains. Ammonites moved through the water in coiled shells. Schools of fish turned beneath the sunlight. Xiphactinus pursued prey through the open sea, while sharks patrolled the same vast hunting grounds. Yet even these animals did not represent the full power of the ecosystem. Beyond the schools and beneath the waves, reptiles descended from land-dwelling ancestors were adapting to permanent life in the water. Some carried long necks through the sea. Others developed immense jaws, muscular tails, and bodies capable of challenging every predator around them. The age of the great marine reptiles was already underway. Long before the Western Interior Seaway divided North America, reptiles had already entered the oceans many times. Their distant ancestors had lived on land and breathed air with lungs. Yet, over millions of years, several unrelated groups returned to the water. Their legs became paddles. Their bodies became more streamlined. Some developed powerful tails, while others evolved 4 broad flippers capable of carrying them through the sea. They never became fish. Every one of these animals still had to rise toward the surface to breathe. They could not extract oxygen from water through gills. However deep they traveled, and however completely adapted they became to marine life, they remained connected to the air above. Within the Western Interior Seaway, these reptiles occupied many different roles. Some pursued fish through open water. Some searched for squid-like animals and ammonites. Others attacked turtles, sharks, or marine reptiles almost as large as themselves. They differed in shape, speed, hunting technique, and the parts of the sea they used. Among the most unusual were the plesiosaurs. The plesiosaur body followed a design unlike that of almost any living marine animal. It had a broad, compact trunk and 4 large flippers. Instead of relying mainly on a tail for propulsion, plesiosaurs moved their limbs through the water. The exact pattern of this movement has been studied using bones, joints, computer models, and comparisons with living animals. They probably used their flippers in a form of underwater flight, producing lift as the limbs swept through the water. The front and rear pairs may have worked together, allowing the animal to move with unusual control. This 4-flippered swimming style was not simply an underwater version of walking. Each limb had become flattened and elongated. The bones of the fingers and toes were enclosed within broad paddles. Strong muscles attached the limbs to the body. With every stroke, the flippers pushed against dense water, carrying the heavy animal forward. Some plesiosaurs had relatively large heads and short necks. These forms are often informally called plesiosaurs, although their evolutionary relationships were more complicated than a simple division between 2 body types. Many were powerful predators equipped with large jaws and robust teeth. Others possessed small heads and extraordinarily long necks. The most famous long-necked forms from the Western Interior Seaway belong to a group called the elasmosaurids. Their necks contained far more vertebrae than those of nearly all other vertebrates. In some species, the neck accounted for more than half the total length of the animal. Elasmosaurus became one of the best-known examples. Its body was massive, but its head was surprisingly small. Between them extended a neck composed of more than 70 vertebrae. The entire animal may have reached around 40 feet in length, although much of that length consisted of the neck rather than the trunk or tail. For many years, artists imagined Elasmosaurus raising its neck high above the water like a swan. Its anatomy makes such a posture improbable. The neck was long, but it was not built to form the tight vertical curves commonly shown in older illustrations. The joints between its vertebrae limited extreme bending, particularly upward movement. The neck was better suited to broad, controlled motion through the water. An elasmosaur may have approached prey without bringing its entire body close. Its small head could move among schools of fish, while the larger trunk remained farther away. The neck might also have allowed the animal to search across a wider area without constantly turning its body. Exactly how it hunted remains uncertain. It may have followed fish from below or from the side. It could have moved its head quickly through a school while using the long neck to adjust direction. Some researchers have suggested that the neck reduced disturbance near the head. allowing the animal to approach prey more quietly. This remains a reconstruction rather than a directly observable fact. Its teeth provide clearer evidence. The jaws of Elasmosaurus contained narrow, pointed teeth suited for gripping slippery animals. They were not built for crushing thick shells or cutting large pieces of flesh. Fish and soft-bodied cephalopods were likely important prey. The head was small enough that it could not swallow the largest animals of the seaway. Instead, Elasmosaurus probably captured prey that could be taken whole. Small stones have sometimes been discovered in the body regions of plesiosaur fossils. These are known as gastroliths when there is evidence that they were swallowed. Their purpose is debated. They may have helped grind food, controlled buoyancy, or simply been swallowed accidentally while the animal fed near the bottom. Different animals may have used them in different ways. Whatever their function, these stones remind us that plesiosaurs were not mythical sea serpents. They were real animals with digestive systems, muscles, injuries, parasites, and daily needs. They had to find food. They had to avoid danger. They had to reproduce in an environment from which some of them may rarely, if ever, have returned to land. Evidence from a pregnant plesiosaur fossil discovered outside the Western Interior Seaway indicates that at least some plesiosaurs gave birth to live young. Returning to a beach to lay eggs would have been extremely difficult for animals with large bodies and rigid flippers. Live birth allowed them to remain fully marine. The known fossil contained a single large developing young rather than many small offspring. This has led to the suggestion that some plesiosaurs may have invested heavily in relatively few young. Whether they provided prolonged care after birth cannot be confirmed, but the possibility changes how these animals can be imagined. A newborn plesiosaur may not always have entered the sea alone among hundreds of siblings. Young animals faced a dangerous world. Their small size made them vulnerable to sharks, large fish, and other marine reptiles. Even adults were not protected from attack. Plesiosaur bones sometimes bear bite marks, and isolated remains suggest that carcasses were scavenged after death. A long neck could help in feeding, but it also created a large exposed target. The sea did not contain one permanent ruling species. Its hierarchy changed over time. Early in the history of the Western Interior Seaway, large fish, sharks, and plesiosaurs occupied many of its highest predatory roles. Later, another group of reptiles entered the sea and transformed its ecosystems. These were the mosasaurs. Mosasaurs were not dinosaurs, and they were not close relatives of plesiosaurs. They belonged to the squamate branch of reptiles, the broad group that also contains modern lizards and snakes. Their earlier ancestors had been much smaller coastal animals. Over a comparatively brief span of geological time, mosasaurs evolved from modest amphibious forms into highly specialized marine predators. Their limbs became flippers, their bodies lengthened, and their tails developed into powerful organs of propulsion. Older reconstructions often showed mosasaurs swimming with straight, snake-like bodies and simple tapering tails. More complete fossils and studies of soft tissue impressions have changed this image. At least some mosasaurs possessed a deep tail with a downward bend in the backbone, supporting a fin-like outline. Rather than moving the entire body in exaggerated waves, they likely generated much of their thrust with the rear body and tail. The front flippers helped control direction and stability. This body plan made mosasaurs effective open water swimmers. Different species, however, were adapted to different prey and styles of hunting. Some had slender jaws filled with narrow teeth for capturing fish and cephalopods. Others possessed stronger skulls and more robust teeth. One specialized form, globidens, had rounded teeth capable of crushing hard shells. It could feed on animals that many pointed-toothed predators could not easily process. Mosasaurs therefore did not represent one ecological role. They diversified into numerous forms, from relatively small hunters to giants approaching the length of a modern bus. They occupied coastal environments, open water, and different levels of the food web. Among the largest and most famous inhabitants of the Western Interior Seaway was Tylosaurus. Its long skull ended in a solid, toothless projection in front of the jaws. Behind it were rows of curved teeth designed to seize prey. Large individuals could reach 40 feet or more in length, although size estimates vary depending on the specimen and the method used. Tylosaurus possessed an elongated body and a powerful tail. It probably cruised through the open sea, searching for fish, sharks, turtles, birds, plesiosaurs, and other mosasaurs. Fossil stomach contents and associated remains show that its diet could be remarkably broad. It was not limited to small prey. A large Tylosaurus was capable of attacking substantial animals. Its teeth could grip and puncture, while movements of the head and body may have helped tear or reposition prey. Smaller animals could be swallowed with limited processing. The mosasaur jaw had a degree of mobility, but it should not be imagined as functioning exactly like that of a modern snake. Mosasaurs possessed flexible connections between some skull elements and an additional joint in the lower jaw. These features helped them manage large prey. However, the popular idea that they could completely dislocate their jaws is inaccurate. Their skulls were mobile but still mechanically connected structures. Their mouths also contained a second set of teeth. On the roof of the mouth were pterygoid teeth, which helped hold prey and move it backward toward the throat. For a struggling fish or squid, escaping after being seized would have been extremely difficult. A mosasaur attack may have happened quickly. A large animal traveling through open water did not need to chase every prey item for a long distance. It could approach from below or behind, accelerate over a limited range, and strike before the target changed direction. But constant violent pursuit would have consumed enormous energy. Much of a predator's life was probably spent moving more slowly, searching and conserving strength. The dramatic moments preserved in bite marks and stomach contents represented only brief parts of days, otherwise filled with swimming, breathing, resting, and following prey. Like plesiosaurs, mosasaurs breathed air. They had to return repeatedly to the surface. A large individual might rise gradually from darker water until its head broke through the waves. After breathing, it would descend again, leaving only a brief disturbance behind. The duration and depth of their dives cannot be measured directly. They may have remained submerged for significant periods, but claims about exact times are speculative. Their lungs, body size, metabolism, and behavior would all have influenced their ability to dive. Mosasaurs probably gave birth to live young. Their fully marine bodies would have made movement on land extremely difficult. Fossils of very young mosasaurs found in offshore deposits support the idea that birth occurred at sea rather than exclusively in sheltered coastal nurseries. The newborn animals were not miniature versions of the largest adults in every respect. Their proportions changed as they grew, and their prey likely changed with them. Small juveniles may have hunted tiny fish and invertebrates while avoiding nearly every large predator around them. Only after years of growth could they enter the upper levels of the food web. Few individuals would have reached maximum size. Disease, injury, starvation, and predation removed animals at every age. A broken jaw or damaged flipper could make feeding impossible. A deep bite might become infected. A weakening animal could fall behind its prey and eventually become prey itself. Fossils preserve evidence of these injuries. Some mosasaur bones show healed fractures or bite marks, proving that the animal survived long enough for new bone to form. Other injuries show no healing and may have occurred near or after death. Bite marks on mosasaur skulls and bodies suggest conflict with other large predators, including members of their own group. These encounters may have involved food, territory, mating, or direct predation. The evidence rarely reveals the exact cause. It records only that powerful jaws closed on bone, and that some animals survived while others did not. The arrival and diversification of mosasaurs increased competition throughout the seaway. Large sharks still hunted there. Xiphactinus remained a formidable fish. Plesiosaurs continued to occupy their own feeding roles. Mosasaurs did not simply erase every earlier predator, but they became increasingly prominent during the late Cretaceous. Each group succeeded in a different way. The long-necked elasmosaur used reach and precise control. Shorter-necked plesiosaurs relied on stronger heads and more direct pursuit. Sharks possessed efficient bodies and teeth continually replaced throughout life. Giant fish used speed and wide jaws. Mosasaurs combined muscular tails, grasping teeth, mobile skulls, and a range of body sizes. The result was not a sea ruled by one monster. It was a complex community of hunters sharing the same enormous space. A school of fish might detect the shadow of an elasmosaur above it. As the fish turned, a shark could approach from the side. A young mosasaur might follow the confusion, looking for an injured animal. Farther below, a larger predator could be watching all of them. Even the hunter that completed the first attack was not guaranteed to keep its meal. Other predators could be drawn by movement, blood, or a struggling body. A carcass became a temporary center of activity. Animals arrived, fed, and left. Fragments sank toward the bottom, where scavengers continued the process. The seaway recycled almost everything, yet there were also long periods of quiet. An elasmosaur moved slowly beneath the surface, its four flippers sweeping through clear water. A mosasaur crossed a deeper channel alone. A turtle rested between breaths. Ammonites drifted through the distance while small fish gathered near the pale seafloor. These animals did not experience themselves as prehistoric. Their world was not lost or ancient. It was immediate and complete. The water around them had always existed. The shoreline seemed permanent. The rhythms of breathing, feeding, migration, and reproduction continued through countless generations. For millions of years, marine reptiles traveled above the buried center of North America. Their bones settled into mud that would one day become dry rock. Their teeth would eventually be found far from any modern ocean. Their skeletons would emerge from Kansas hillsides, South Dakota badlands, Canadian plains, and the exposed formations of the American West. They remain there because the vanished sea recorded their lives. And beneath its warm surface, the competition between these great reptiles was only one part of a much larger world, extending from the deepest water to the distant shores. The farther one traveled toward the shores of the Western Interior Seaway, the more the world began to change. The endless horizon of open water gradually gave way to shallow bays, winding estuaries, muddy river mouths, and broad coastal plains. Salt water mixed with fresh water, carried from distant mountains. Marshes spread across low ground. Dense forests stood only a short distance from quiet lagoons, while beyond them, enormous dinosaurs wandered through landscapes that would one day become the center of North America. The boundary between sea and land was never a single line. Every tide reshaped the shoreline. Every storm carved away one stretch of beach while building another. Rivers delivered fresh sediment day after day, slowly extending deltas into the sea. In other places, rising water reclaimed the land just as steadily, drowning forests and creating new shallow bays. The coast itself seemed alive. It expanded and contracted through time, never remaining exactly where it had been before. A place that served as dry ground for thousands of years could eventually disappear beneath salt water. Millions of years later, the same location might once again become part of the continent. These changing coastlines became some of the richest environments in the entire Western Interior Seaway. Fresh water brought nutrients from the land. Warm sunlight penetrated the shallow water. Marsh plants stabilized muddy ground, while countless invertebrates fed within the sediment. Small fish gathered in extraordinary numbers, protected from the strongest waves. Estuaries and lagoons served as nurseries where young fish could grow before venturing into deeper water. Crustaceans searched through mud. Mollusks buried themselves beneath the surface. Insects hovered above reeds and flowering plants. Every level of the food web became concentrated near the shore. Large predators understood this well. Sharks frequently entered coastal waters in search of schools of fish. Juvenile mosasaurs hunted in shallower environments than many adults. Sea turtles moved between feeding grounds, while long-necked plesiosaurs occasionally approached the coast where prey became especially abundant. But the shoreline did not belong only to marine animals. Beyond the beaches stretched one of the most remarkable landscapes of the late Cretaceous. On the western side of the sea lay Laramidia. Although much narrower than modern western North America, Laramidia supported an astonishing diversity of life. Mountain ranges rose in the distance, where tectonic forces continued to reshape the continent. Rivers descended toward the coast, feeding broad floodplains covered by forests, ferns, flowering plants, conifers, and wetlands. Large dinosaurs walked within sight of the sea. Herds of duck-billed hadrosaurs browsed on abundant vegetation. Horned dinosaurs moved through open areas, their elaborate skull ornaments differing from species to species. Armored ankylosaurs searched for low-growing plants, while protecting themselves beneath heavy bony plates. Towering above many of them were titanosaurs in some southern regions, while smaller dinosaurs occupied nearly every available habitat predators followed. Different tyrannosaur relatives ruled different parts of Laramidia through time. They were not all identical to the famous Tyrannosaurus rex, which would appear only near the very end of the Cretaceous. Earlier ecosystems contained formidable hunters such as Gorgosaurus, Daspletosaurus, and other closely related tyrannosaurs. Each region possessed its own balance between herbivores and carnivores. The sea influenced all of them. Moist coastal climates encouraged lush vegetation. Rivers carried nutrients across floodplains. Seasonal flooding reshaped forests and created temporary lakes where countless animals gathered to drink. Sometimes floods carried more than water. A fallen tree could be swept downstream toward the sea. Entire logs drifted into coastal bays before becoming waterlogged and sinking to the bottom. Occasionally, the same happened to animals. A dinosaur that died beside a river might be carried toward the coast during seasonal flooding. Most remains were scattered long before reaching the open sea. Yet, under favorable conditions, some bones continued their journey into marine environments. This is why paleontologists occasionally discover dinosaur fossils preserved within marine rocks. The animals had not lived in the sea. Instead, rivers became the final connection between two entirely different worlds. Across the water, another continent faced the same sea. To the east lay Appalachia. Millions of years earlier, eastern North America had been connected directly to the west. Now, the Western Interior Seaway separated them by hundreds of miles of warm saltwater. The dinosaurs living on each side could no longer move freely between the continents. Over millions of years, this isolation influenced evolution. Species living in Laramidia continued changing independently from those in Appalachia. Although both continents shared ancient ancestors, their ecosystems gradually developed distinct characteristics. The fossil record from Appalachia is less complete than that of Laramidia. Much of the eastern continent has experienced erosion or remains buried beneath younger deposits, making discoveries more difficult. Even so, enough fossils have been found to reveal a different community of dinosaurs. Large duck-billed dinosaurs lived there. Armored dinosaurs continued browsing through forests. Predatory dinosaurs occupied the highest positions in the food web, although some belonged to groups that had become uncommon farther west. The sea had become an evolutionary barrier. It did not merely separate geography, it separated entire histories. Generation after generation, animals born on one continent never encountered those living across the water. Forests evolved independently. Rivers followed different courses. Plants spread according to local climates. The same sunlight warmed both shores. Yet the two continents slowly became different worlds. Between them stretched the inland sea. Above its waters, another community moved almost continuously through the sky. Large pterosaurs drifted on rising air currents generated by warm coastal winds. Among the most familiar was Pteranodon. Its wings extended more than 20 feet from tip to tip, allowing long periods of efficient gliding above the waves. Rather than beating its wings constantly, it could travel remarkable distances by using the movement of the air itself. The broad surface of the seaway created ideal conditions for soaring flight. Warm air rose from heated coastlines, cooler marine air moved inland, storm systems generated powerful winds capable of carrying large flying reptiles across enormous distances. Pteranodon searched these waters for fish. Exactly how it captured prey remains uncertain. It probably seized fish near the surface rather than continuously skimming through the water, as older illustrations often suggested. Once successful, it could swallow relatively small prey before continuing its flight. Its greatest advantage was not speed, it was efficiency. While marine reptiles remained confined to the water below, Pteranodon could travel from one coastline to another with comparatively little effort, observing vast stretches of sea from above. Smaller pterosaurs shared portions of the same sky. Different wing shapes, body sizes, and feeding strategies reduced direct competition. At the same time, true birds were becoming increasingly successful. Some still possessed teeth inherited from their dinosaur ancestors. Ichthyornis flew with rapid wing beats over coastal waters, capturing small fish with surprising agility. Although it resembled certain modern seabirds at first glance, its toothed jaws revealed how early birds still retained many ancient features. Another remarkable bird chose an entirely different lifestyle. Hesperornis almost abandoned flight altogether. Its wings became greatly reduced, while its legs transformed into powerful underwater propellers. Instead of soaring through the sky, Hesperornis pursued fish beneath the surface. It moved awkwardly on land but became an accomplished diver within the water, demonstrating that birds were already exploring very different evolutionary paths. Along quiet beaches, these animals occasionally occupied the same coastline. Pterosaurs rested after long flights. Birds searched tidal pools. Small reptiles hunted insects among vegetation. Dinosaurs left footprints in wet sand, only a short distance from where marine shells accumulated with every incoming tide. The boundary between land and sea became written into the sediment itself. Some layers preserved ripple marks created by shallow waves. Others contained dinosaur tracks crossing muddy flats. Nearby appeared shells of oysters, clams, and ammonites. Together they recorded moments when marine and terrestrial worlds overlapped. Storms strengthened this connection. Dark clouds gathered over the warm sea before moving inland. Heavy rain swelled rivers beyond their banks. Floodwaters spread across floodplains, uprooting vegetation and carrying enormous quantities of sediment toward the coast. When those swollen rivers finally entered the sea, they transformed the shoreline. Fresh water pushed outward over denser salt water. Mud colored the shallows brown. Logs floated among drifting vegetation. Fish followed nutrients carried from inland forests. Soon larger predators arrived as well. For several days after major floods, coastal ecosystems became exceptionally productive. Then conditions slowly returned to normal until the next seasonal cycle began. Year after year, these rhythms continued. Animals adapted to them without understanding the immense geological forces operating beneath their feet. They could not know that the mountains supplying the rivers continued rising. They could not know that the sea itself would one day disappear. To every creature living beside its shores, the Western Interior Seaway appeared permanent. Generations were born, hunted, reproduced, and died without witnessing any noticeable change in the coastline. Yet across millions of years, the continent continued to move. The mountains grew higher, sediment accumulated, the sea gradually became shallower. The first signs of an ending had already begun, although no animal could possibly recognize them. The great inland sea had divided a continent and created one of the richest ecosystems North America would ever know. Now, slowly and almost invisibly, the forces that had built it were preparing to erase it. For millions of years, the Western Interior Seaway did more than separate water from land. It divided an entire continent. To the west lay Laramidia, a long, relatively narrow strip of land bordered by the young mountains that would eventually become part of the Rocky Mountains. To the east stretched Appalachia, lower, older, and heavily forested. Between them extended hundreds of miles of warm, shallow sea. No bridge connected the two. No great migration could simply cross from one side to the other. The inland sea became a barrier, every bit as real as an ocean. To modern eyes, North America appears whole. Roads, rivers, forests, and cities connect east and west without interruption. Looking at a map, it can be difficult to imagine that one of the largest continents on Earth once existed as two separate landmasses. Yet for much of the late Cretaceous, that was reality. Animals born on one side of the seaway would never encounter those living across the water. Their ancestors had once shared the same continent, millions of years earlier, but as generations passed, isolation slowly began to reshape life. Evolution often works most powerfully when populations become separated. When individuals can no longer interbreed, each population responds independently to its own environment. Different climates, predators, food sources, and random genetic changes gradually produce new species. The Western Interior Seaway created exactly these conditions. Laramidia was relatively small in area compared with the eastern continent, yet it became astonishingly rich in dinosaur diversity. One valley could contain species that never spread far beyond their local region. A neighboring river system might support closely related animals that looked similar at first glance, but differed in horns, crests, body proportions, or behavior. Paleontologists still debate why this happened. One possibility is that mountains, rivers, changing coastlines, and climate divided western habitats into many smaller ecological regions. Even without vast distances, populations could remain separated long enough to evolve independently. The result was extraordinary diversity. Duck-billed hadrosaurs flourished throughout many parts of Laramidia. Some carried long, hollow crests projecting behind the skull. Others possessed broad, solid crests, or none at all. These structures may have produced sounds, helped individuals recognize members of their own species, or served as visual displays during courtship. No one can hear their voices today. Only the bones remain. Computer models suggest that at least some hollow crests could have acted as resonating chambers, but exactly what these animals sounded like remains unknown. Nearby lived the ceratopsians. These horned dinosaurs became some of the most recognizable animals of the late Cretaceous. Massive skulls carried elaborate frills extending behind the head, often decorated with spikes, hooks, or rounded projections. The horns themselves varied enormously. Some species possessed long forward-pointing brow horns. Others developed shorter horns combined with highly ornamented frills. Many of these features probably served several purposes simultaneously, including display, species recognition, and perhaps defense. Their skulls were living architecture. Each species carried its own distinctive design. To another ceratopsian, these differences may have communicated age, health, maturity, or reproductive fitness. To modern paleontologists, they help distinguish one species from another millions of years later. Among the forests and floodplains also wandered armored ankylosaurs. Heavy bony plates covered their backs, while many species carried powerful tail clubs capable of delivering tremendous force. Contrary to older illustrations, these animals were probably not slow-moving, living tanks, constantly dragging themselves across the landscape. Their bodies were low and heavily built, but their limbs suggest that they could move effectively while feeding through dense vegetation. Predators had good reason to approach cautiously. A well-placed swing from an ankylosaur's tail may have been capable of breaking bones. Exactly how often such defensive blows occurred cannot be determined, but the weapon itself represents one of the most specialized defensive structures ever evolved by a land vertebrate. Above all these herbivores stood the great predators. During much of the late Cretaceous, Laramidia was home to several species of tyrannosaurs, closely related to the later Tyrannosaurus rex. Gorgosaurus hunted farther north. Daspletosaurus occupied other regions. Near the end of the Cretaceous, Tyrannosaurus itself appeared, becoming one of the largest terrestrial predators in Earth's history. These animals did not coexist everywhere at the same time. Different species replaced one another through millions of years as environments continued changing. The fossil record compresses this immense span into neighboring rock layers, making it easy to imagine them sharing the same landscape even when they lived hundreds of thousands or even millions of years apart. Time is often the greatest distance preserved in stone. The western continent also supported smaller predators. Swift dromaeosaurs hunted beneath forest canopies. Troodontids searched for small prey with keen senses. Early mammals remained mostly small but increasingly diverse, feeding on insects, seeds, fruits, and perhaps small vertebrates. They lived in the shadow of dinosaurs. Few would have attracted much attention from the giant herbivores surrounding them. Yet these tiny mammals represented lineages that would eventually inherit the world after the dinosaurs disappeared. Laramidia was not merely a dinosaur paradise. It was an entire ecosystem containing insects, flowering plants, conifers, crocodilian relatives, turtles, snakes, lizards, amphibians, birds, mammals, and countless organisms that rarely become fossils. Every fallen tree supported insects. Every river sheltered fish. Every forest echoed with sounds that have vanished forever. Across the inland sea, Appalachia followed its own path. The eastern continent differed in important ways. Its mountain ranges were older and lower than those rising in the west. Broad forests covered much of the landscape, while rivers flowed eastward toward the Atlantic and westward into the inland sea. Unfortunately for paleontologists, much of Appalachia's geological history has proven difficult to preserve. Later erosion removed many late Cretaceous deposits. Dense vegetation, modern development, and younger sediments conceal many remaining rocks. As a result, the fossil record from eastern North America is far less complete than that of Laramidia. But incomplete does not mean empty. Important discoveries continue to emerge. Duck-billed dinosaurs live throughout Appalachia. Although they belong to somewhat different evolutionary branches than many Western relatives, primitive armored dinosaurs persisted longer than expected. Large predatory dinosaurs included forms unlike the dominant tyrannosaurs of Western North America. Some belonged to older lineages that had disappeared elsewhere. Isolation had preserved evolutionary histories in surprising ways. The sea acted as both a barrier and a filter. Only flying animals could routinely cross it. Pterosaurs drifted above both continents. Birds traveled between coastlines. Insects occasionally dispersed with favorable winds. Seeds floated across water or were carried by storms. For most large land animals, however, crossing hundreds of miles of open sea was impossible. The separation lasted long enough for entire ecosystems to diverge. If one could somehow stand high above the Western Interior Seaway during the late Cretaceous, the difference would not immediately appear dramatic. Both coastlines contained forests. Both supported rivers. Dinosaurs lived on each side. Yet beneath those similarities, evolution had been writing two different stories for millions of years. The Western chapter emphasized extraordinary diversity among horned dinosaurs, hadrosaurs, tyrannosaurs, and armored herbivores. The Eastern chapter preserved older lineages while following its own quieter evolutionary path. Neither continent remained completely stable. Sea levels rose and fell repeatedly. Coastal plains expanded before flooding once again. River systems shifted. Volcanic ash occasionally settled across broad regions. Wildfires likely passed through forests during dry seasons, opening space for new vegetation. Life responded continuously. Species migrated locally. Populations expanded and contracted. Some disappeared entirely while others diversified. Most of these changes occurred so gradually that no individual animal could perceive them. A hadrosaur born beside one river would live and die believing its homeland had always existed exactly as it appeared. Generation after generation inherited landscapes already transformed by thousands of years of invisible geological change. The greatest architects of this world were not the dinosaurs. They were the mountains to the west. Tectonic forces continued lifting young ranges higher. Rain and rivers immediately began wearing those mountains back down. Gravel, sand, and fine mud traveled eastward through enormous river systems before entering the inland sea. Every grain of sediment slightly altered the basin. Shallow areas slowly expanded. New deltas formed. Older coastlines disappeared beneath accumulating deposits. The process seemed unimaginably slow. Yet given enough time, entire seas can vanish through exactly such accumulation. At first, these changes affected only local landscapes. A bay became slightly shallower. A marsh expanded. A river changed course. The sea still appeared endless. Marine reptiles still hunted offshore. Pterosaurs continued gliding above the waves. Dinosaurs still walked along beaches where shells accumulated with every tide. Nothing suggested that the entire inland sea was approaching its final chapter. But beneath the surface, the balance had begun to change. Mountain building continued supplying sediment faster than before. global sea levels no longer remained as high as they once had. Together, these forces gradually reduced the space available for the inland waters. The change could not be seen within a lifetime, nor within 100 generations, but over millions of years. Shorelines migrated. The distance between east and west slowly decreased. Habitats that had existed since the beginning of the seaway became fragmented. Some marine species adapted, others shifted their ranges. Still others quietly disappeared from regions where they had flourished for ages. The continent itself was beginning to reunite. No animal understood this transformation. To every creature alive, tomorrow looked much like yesterday. Only the rocks would remember that the greatest geographical change in North America since the sea first appeared had already begun. The Western Interior Seaway had divided a continent. Now, almost imperceptibly, the continent was preparing to become one again. The reunion would not happen suddenly. It would unfold grain by grain, river by river, shoreline by shoreline, until one of Earth's greatest inland seas existed only in memory preserved beneath layers of stone. Nothing in nature disappears overnight. The Western Interior Seaway had taken millions of years to form, and it would require millions more to fade away. Its disappearance was not marked by a single dramatic event, but by countless small changes that accumulated so slowly no living creature could ever witness the entire transformation. For generation after generation, the sea seemed eternal. The tides continued to rise and fall. Marine reptiles hunted beneath the surface. Pterosaurs glided above the waves. Dinosaurs browsed along distant coastlines. The familiar rhythms of life continued almost unchanged. Yet the continent beneath them was still moving. Far to the west, enormous tectonic forces continued, lifting the young Rocky Mountains. Every year, rain, snow, rivers, and floods carried fragments of those mountains downhill. Pebbles became gravel. Gravel became sand. Sand became fine mud. Eventually, nearly all of it reached the sea. River after river delivered fresh sediment into shallow bays and estuaries. Deltas slowly expanded. Channels shifted their courses. Marshes spread across ground that had once been open water. The changes were almost impossible to notice. A shoreline might move only a few feet during many human lifetimes. A shallow lagoon gradually became a marsh. A river abandoned one channel and created another nearby. To the animals living there, the landscape appeared permanent, but geological time tells a different story. Every grain of sediment remained behind after the floodwaters retreated. Each layer made the basin slightly shallower than before. Millions upon millions of these tiny deposits slowly altered the shape of an entire continent. The sea was not simply drying up, it was being filled. At the same time, another process was unfolding across the globe. During much of the Cretaceous period, sea levels had been among the highest in Earth's history. Vast portions of today's continents lay beneath shallow oceans, but these unusually high sea levels did not remain constant forever. Gradually, they began to fall. Scientists continue investigating the exact balance between global sea level changes and regional tectonic activity, but together, these processes steadily reduced the size of the Western Interior Seaway. The ocean no longer reached as far inland as it once had. Shallow coastal environments expanded first, then deeper channels became narrower. Former islands merged with growing coastlines. Places that had once required days of flight to cross gradually became connected by continuous land. For marine life, these changes created entirely new challenges. Some animals adapted by following the retreating shoreline. Others remained within shrinking marine habitats that became increasingly isolated from one another. Changes in water circulation altered oxygen levels in some regions. Nutrient pathways shifted. Food webs that had remained stable for millions of years slowly reorganized. No single species experienced these changes in exactly the same way. Some populations expanded into newly formed coastal wetlands. Others found their breeding grounds disappearing beneath river sediment. Predators followed prey into unfamiliar environments. Competition increased where habitats became smaller. Even tiny environmental changes could ripple through entire ecosystems. A slightly shallower bay warmed more quickly during summer. A river carrying more fresh water reduced local salinity. New vegetation stabilized coastlines that had previously been open beaches. Each alteration influenced countless organisms living nearby. The great marine reptiles also faced a changing world. Mosasaurs continued ruling many parts of the sea, but the environment supporting them was becoming less extensive. Large predators require enormous amounts of food. As habitats shrink, prey distributions change as well. Some mosasaur species remained remarkably successful until the very end of the Cretaceous. Others became increasingly restricted in where they could thrive. Plesiosaurs experienced similar pressures. Their ancient lineage had survived for well over 100 million years. They had witnessed changing continents, shifting oceans, and countless evolutionary experiments. Now, they occupied seas that were themselves becoming increasingly fragmented. Marine turtles continued crossing coastal waters. Sharks still patrolled estuaries and open channels. Schools of fish remained abundant in many places. To an observer watching only a single generation, nothing appeared unusual. The ecosystem still functioned. Life still flourished. The approaching end remained invisible. Meanwhile, the land continued expanding. Forests gradually occupied areas that had once belonged to shallow lagoons. Freshwater rivers carved channels through newly exposed sediment. Floodplains widened. Wetlands shifted toward the retreating coast. The continent slowly reclaimed territory that had been underwater for millions of years. New habitats appeared almost as quickly as old ones vanished. Young forests spread across fresh ground. Flowering plants colonized recently exposed soil. Insects followed. Small mammals explored habitats unavailable to previous generations. Dinosaurs extended their ranges into landscapes that had once been covered by warm salt water. The retreating sea did not leave behind an empty wasteland. It created opportunities. Every newly exposed plain became another place where life could establish itself. The changing geography also altered climate on a regional scale. Large bodies of water store heat efficiently. As the inland sea became smaller, seasonal temperature differences across central North America gradually increased. Rainfall patterns shifted. Winds followed different paths. River systems responded by changing both their courses and their seasonal behavior. Climate never stands completely still. Even small changes influence vegetation, migration, reproduction, and survival. Countless generations of animals adjusted without realizing why conditions slowly differed from those experienced by their ancestors. Far offshore, marine sediments continued accumulating quietly. The remains of plankton settled through the water day after day. Tiny shells collected on the seafloor, fish skeletons, ammonite shells, shark teeth, and fragments of marine reptiles slowly disappeared beneath fresh layers of mud. Each year added only a thin covering. Over millions of years, those thin layers became hundreds of feet thick. They preserved one of the richest records of marine life anywhere in North America. The rocks remembered everything. Animals did not. Entire species appeared, flourished, and disappeared, while the sediment below silently recorded their existence. Many of the fossils discovered today owe their remarkable preservation to these calm depositional environments created during the final stages of the inland sea. As the sea continued retreating, fewer marine sediments accumulated across central North America. Reefer deposits became increasingly common. Sandstones replaced offshore chalk in many regions. Freshwater environments occupied areas once dominated by saltwater ecosystems. The continent was changing chapter by chapter. Eventually, the Western Interior Seaway no longer formed one continuous body of water. Instead, separate marine basins remained connected only intermittently. Some became isolated for long periods. Others disappeared completely beneath advancing river plains. The once vast inland sea had become a collection of shrinking remnants. Its greatest age had passed, yet another event approached, one completely unrelated to the gradual retreat of the sea itself. Far beyond Earth, an asteroid continued traveling silently through space. No creature swimming in the inland sea could possibly know that it existed. No pterosaur gliding above the coast could see it approaching. Its journey had begun millions of miles away. For now, however, life continued almost normally. Mosasaurs still hunted, sharks still circled schools of fish, birds crossed the quiet bays, dinosaurs wandered newly expanded coastal plains. The world remained astonishingly rich with life. The coming catastrophe had not yet arrived. The Western Interior Seaway was already fading for geological reasons, but before its slow disappearance could fully reshape North America, another event would forever change the history of every ecosystem on Earth. The sea had survived shifting continents. It had survived changing climates. It had survived tens of millions of years of evolution. Its final chapter would be written under a sky unlike any that had come before. And when that moment arrived, neither the sea nor the creatures that depended upon it would ever be the same again. The end of the Western Interior Seaway was not the end of water in the center of North America. Rivers still crossed the plains. Lakes filled low areas. Marshes spread across floodplains, and shallow marine remnants lingered in parts of the north. But the immense body of salt water that had once connected the Arctic Ocean with the Gulf was losing its continuity. East and west were becoming one continent again. The transformation took place so gradually that there was no final wave retreating beyond the horizon. No single morning arrived when the sea was suddenly gone. Instead, each generation inherited a shoreline slightly different from the one known by its distant ancestors. A bay became a marsh became a river plain. Sediment covered the shells beneath it. Forests spread across the new land, and the memory of open water disappeared from the living world. The last inhabitants of the inland sea continued their lives within this changing geography. Fish moved through the remaining channels. Sharks followed them into coastal waters. Ammonites still drifted through the sea. Their coiled shells divided internally into chambers. Mosasaurs remained among the largest predators in the ocean, while long-necked plesiosaurs survived in marine environments elsewhere. These animals had endured enormous changes before. Their lineages had survived shifting continents, altered climates, and repeated transformations of the oceans. To them, the shrinking inland sea was not necessarily a sign that an entire age was approaching its conclusion. Life does not recognize geological boundaries. It simply continues until conditions no longer allow it to do so. Near the end of the Cretaceous period, approximately 66 million years ago, an asteroid several miles across struck the region now occupied by the Yucatan Peninsula. The impact released energy on a scale almost impossible to imagine. Rock was shattered, melted, and thrown high into the atmosphere. Powerful earthquakes moved through the planet. Near the impact site, enormous waves crossed surrounding seas, while fires spread across some landscapes. But the most lasting effects came after the immediate destruction. Dust, sulfur-rich material, and other debris entered the atmosphere, reducing the amount of sunlight reaching Earth's surface. Temperatures fell. Photosynthesis declined on land and in the oceans. Plants and plankton stood at the foundation of nearly every major food web. When primary production collapsed, the effects moved upward. Herbivores lost food. Small predators lost prey. Large predators, which required the greatest amount of energy, became especially vulnerable. The extinction did not affect every organism equally. Some species disappeared quickly. Others survived the first months, but could not reproduce successfully under the new conditions. Populations already limited in size or geographic range were particularly exposed. In the oceans, ammonites vanished completely. Mosasaurs disappeared. Plesiosaurs disappeared. Many species of marine plankton were lost, along with numerous other organisms that had shaped Cretaceous seas for millions of years. On land, all non-avian dinosaurs became extinct. The flying pterosaurs vanished as well. Birds survived, but only a small portion of their diversity crossed the boundary into the new era. Mammals, crocodilians, turtles, amphibians, fish, insects, and plants also suffered severe losses. Yet some representatives survived. The Western Interior Seaway was already retreating before the asteroid struck. Its disappearance, therefore, cannot be explained by the impact alone. Mountain building, sediment accumulation, changing ocean basins, and falling sea levels had been reshaping North America for millions of years. The asteroid did not drain the inland sea. Instead, it ended the great Cretaceous ecosystems that had lived within and beside its remaining waters. The geography was already changing. Now the life inhabiting that geography changed with extraordinary speed. After the extinction, the world did not remain silent forever. Sunlight gradually returned. Plants spread across damaged landscapes. Rivers continued flowing. Surviving animals reproduced, and ecosystems began rebuilding themselves from the lineages that remained. But the world that emerged was fundamentally different. No mosasaur rose through the water, no ammonite shell moved beneath the waves, no pteranodon crossed the sky, no herd of giant non-avian dinosaurs approached the shore. The familiar inhabitants of the Cretaceous had become part of the past during the early Cenozoic era. The final remnants of the inland sea withdrew from the northern Great Plains. Sediment continued to spread eastward from rising western highlands. Rivers crossed areas that had once formed the seafloor. The continent was whole again. Yet the ancient sea had not truly vanished. It had changed form. Its mud became shale. Its accumulated carbonate remains became chalk and limestone. Its beaches and river deltas hardened into sandstone. The water disappeared, but the sediments it left behind remained beneath the landscape. In western Kansas, pale cliffs rise from the plains in formations such as the Smoky Hill Chalk. They appear dry, pale, and quiet beneath the modern sky. Grass grows above them. Wind passes across the open ground. There is no salt water for hundreds of miles. Yet the rock itself was formed within an ancient sea. Much of the chalk began as the microscopic remains of organisms living near the surface. After death, their tiny calcium-rich structures sank through the water and accumulated on the bottom. The process continued for immense spans of time, layer after layer compressed beneath newer sediment until the soft seafloor became solid rock. Within those layers were buried the remains of larger animals. Fish skeletons settled into the mud. Shark teeth fell from jaws and disappeared beneath sediment. Ammonite shells sank after death. Turtles, birds, pterosaurs, plesiosaurs, and mosasaurs occasionally entered the fossil record. Most bodies were destroyed before burial. Scavengers consumed them. Currents scattered their bones. Chemical processes dissolved them. Only a tiny fraction survived long enough to fossilize. This rarity gives each discovery extraordinary value. A vertebra may reveal the size of an animal. A tooth can suggest what it ate. A healed fracture records an injury survived during life. Stomach contents preserve the remains of a final meal. Together, such details allow paleontologists to reconstruct not only the appearance of extinct animals, but portions of their behavior and ecology. During the 19th century, fossil hunters began uncovering remarkable marine skeletons across the Great Plains. Kansas became especially famous. At first, finding the bones of enormous sea reptiles in the center of a continent seemed almost impossible. Their presence challenged familiar ideas about the history of the landscape. But the rocks told a consistent story. Marine shells appeared beside fish. Fish appeared beside mosasaurs. Layers stretched across multiple states. The only reasonable explanation was that the plains themselves had once lain beneath the sea. As more fossils were collected, the lost ecosystem slowly returned in scientific imagination. Individual bones became skeletons. Skeletons became species. Species became food webs. The layers surrounding them revealed water depth, temperature, oxygen conditions, storms, coastlines, and the changing chemistry of the sea. The landscape became readable. A paleontologist walking through dry badlands or chalk exposures is not simply searching for an isolated object. Every fragment occupies a position within a layer. Its orientation may reveal the direction of a current. The surrounding sediment may show whether the animal settled in quiet offshore water or was transported by a storm. Nearby fossils indicate which organisms shared the environment. Removing a specimen without recording this context would erase part of its history. Modern researchers therefore map discoveries carefully. They study bones using microscopes, chemical analysis, medical imaging, and three-dimensional models. Collections gathered generations ago can be examined again with techniques their discoverers could never have imagined. Even fossils already resting inside museums continue producing new information. A skeleton may be re-identified, a mark once dismissed as damage may prove to be a bite. The internal structure of a bone may reveal growth rate or age. Chemical traces can provide clues about water conditions and movement between habitats. The ancient sea continues to change as a scientific idea because every discovery adds another piece to the reconstruction. Its legacy also extends beyond fossils. Sedimentary basins associated with the Western Interior Seaway contain deposits of coal, oil, and natural gas. Organic material buried within ancient mud was altered by heat, pressure, and time. In suitable geological settings, hydrocarbons accumulated within porous rock beneath impermeable layers. These resources later became deeply connected with the economies and development of modern North America, but they began within ancient environments. Some carbon came from organisms too small to see without magnification. Their remains sank into oxygen-poor sediment, were buried, and remained trapped for tens of millions of years. Energy captured from Cretaceous sunlight became stored within stone. The inland sea also influenced the soils, groundwater systems, minerals, and physical terrain of the Great Plains and the Rocky Mountain region. Roads cut through its sediments. Farms occupy land formed partly from weathered marine rock. Cities stand above layers containing shells and bones from animals that lived before mammals became dominant. People cross the ancient seafloor every day without realizing it. A journey through central North America may pass above the former habitats of ammonites, sharks, marine birds, and giant reptiles. A hill beside the highway may represent offshore mud. A pale rock exposed in a drainage ditch may contain fragments of shells. The surface belongs to the present, but the ground beneath it holds a much older geography. The most remarkable evidence is sometimes almost ordinary. A small spiral ammonite found within stone, a shark tooth weathering from a hillside, a thin layer of chalk beneath grass. Each object is a surviving detail from a world too vast to preserve in full. No fossil can restore the sound of waves crossing the inland sea. It cannot reproduce the color of the water, the movement of clouds, or the exact pattern of light across a mosasaur's skin. The fossil record is incomplete. Most species left no remains at all. Most individual animals disappeared without a trace. Soft tissues, colors, sounds, social behavior, and countless daily interactions have been lost. Scientific reconstruction therefore exists between evidence and uncertainty. Bones establish anatomy. Rock layers establish environment and time. Comparisons with living animals suggest possible movement or behavior. Beyond that point, conclusions must remain cautious. The vanished sea can never be observed directly, yet its existence is not speculation. Its sediments stretch across the continent. Its fossils appear in predictable layers. Its shorelines can be traced through sandstone, shale, coal, and marine deposits, evidence from thousands of locations joins into one coherent history. North America was divided. A sea occupied its center. Marine animals lived where plains now extend. The mountains rose, the water retreated, and the continents on either side became connected once again. Today, the Great Plains seem almost like the opposite of an ocean. They are defined by distance, grass, open sky, and an enormous horizon. Storms move across them invisible walls. Wind bends the vegetation in long waves. In this movement, there is something strangely familiar. The grass follows the wind as water once did. Cloud shadows pass over fields that were once sea floor. The horizon remains wide and uninterrupted, much as it appeared above the ancient sea. Only the surface has changed. Beneath the roots of modern plants lie layers formed from countless organisms that drifted through warm Cretaceous water, far below roads and towns. Marine sediments preserve the outline of a continent that no longer exists. Laramidia and Appalachia have become geographical memories. Their separating sea has become rock, but the history remains. It waits in cliffs, museum drawers, quarries, riverbanks, and quiet exposures across the plains. A child may hold a shark tooth found hundreds of miles from the nearest ocean. A paleontologist may uncover the vertebra of a mosasaur beneath a Kansas hillside. For a moment, the modern landscape opens. The grass disappears. The plains sink beneath warm water. Ammonites drift in the distance. Fish move through the sunlight. A dark shape passes below, then vanishes into deeper blue. Above the waves, a pterosaur turns into the wind. Along two distant shores, dinosaurs walk across separate continents. And for a brief moment, one of the greatest lost seas in Earth's history exists again.